So a quick note on our agenda for today. We're going to cover some key market trends in industrial connectivity before looking at a high-level overview of the various aspects of factory connectivity. We'll then take a look at some of the enabling technologies for this. We're going to start with OS485 for traditional field bus and multi-point LVDS for backplane. Then Conrad's going to take us through IO-Link, which is changing the way in which we communicate with sensors that are at the factory edge today. Hector's going to then take us into a deep dive into Ethernet connectivity and how this is evolving for use in industrial environments with robustness, determinism, and the new two-wire Ethernet solution. Then we'll introduce some options that were announced this year for galvanic isolation, specifically on high-speed USB ports, and then we'll just wrap up with some conclusions. So the future is increased connectivity. Well, what do we mean by this? So let's take a look at the industrial automation and intelligent building market and the trends that are driving the need for increased connectivity. The smart factory, industrial IoT, we've all heard these buzzwords around Industry 4.0. That's promising to change the way in which we create products thanks to the digitization of our manufacturing and process facilities. The problem is manufacturers are under increasing pressure to operate with agility, aim to respond to changing customer and macroeconomic demand, and doing this all the while maintaining overall productivity and cost effectiveness. This all needs to be achieved facing the challenge of shorter product life cycles, got more product variations. This is driving smaller quantity runs and longer lead times in the supply chain. So what Industry 4.0 or smart manufacturing or smart factory is all about is really addressing this by fueling your factory and your automation systems with more and more meaningful data. This data is created with smarter sensors, smarter robotics, and then taking this data and leveraging it with techniques like machine learning and artificial intelligence. This data allows you to capture new insights into the equipment and manufacturing process, allows for better decision making, more efficiency, and provides real-time flexibility. Of course, this connectivity is not just applicable to the factory floor, but it pertains to the design of intelligent buildings as well. And a very interesting statistic today, 40% of all energy consumption is actually within buildings, which makes buildings one of the keys to reducing global energy consumption. So trying to capture new and better insights from building assets, this is going to drive improvements in all aspects of building management and energy efficiency, from things like HVAC to lighting. And whether you're in an office block or in a factory floor, to enable this expansion in productivity will require seamless connectivity. With a absolute myriad of interfaces and solutions, realizing this connectivity, it's not a trivial task. But today we're going to cover some of the latest options available. And we'll discuss the key trends that we see in communication networks, which are happening to address this need for connectivity. Today, the reality is there are a host of edge devices within buildings and factories with very limited connectivity. They have limited or no real-time configurability, and there's no auxiliary information being collected or communicated. What we want to do is make all of these devices become interconnected. Today's talk is all about how we deliver this seamless edge-to-cloud connectivity with new technologies like Industrial Ethernet and IO-Link, while maintaining high-performance field bus networks and backplanes in your existing systems as you go through this transition phase of this connectivity revolution. Let's dive a bit deeper into these key market trends that we are seeing. The first is a very clear overall demand for more connectivity between more devices, and this has been driven by several factors. Firstly, as the number of sensors deployed at the edge is increasing, this is naturally driving the requirement for more bandwidth in the connectivity infrastructure to the edge nodes. With more sensors and more ports, more I/O found on industrial control systems, the need for networks which can support higher number of devices and higher number of nodes is critical. There's also a shift towards harmonization of the networks across the factory floor. Traditionally, the industrial networking domain has been a fragmented space with parallel vendors-driven communication protocols. This is inherently incompatible with one another. This fundamentally creates a barrier to the seamless connectivity across the factory. By consolidating the various flavors of networks used, this eases the burden on complex gateways and minimizes the barrier to seamless connectivity. And finally, as the complexity and precision of the sensors at the edge increases, this is again further driving a need for the amount of data that has to be gathered and moved around. So one example, easy to think, is in a robotics and control system where you want to have a higher accuracy control. This means more resolution, therefore means more bandwidth requirements. And with this in mind, today's communication systems must be rolled out while thinking about tomorrow's bandwidth requirements. And so a system and an interface or a communication infrastructure that is scalable and easily upgradable is similarly important. So to get a sense of the scale of the challenge here, we'll look at something that's just, you might find at the edge of a factory. For example, here we've got a factory conveyor belt. And so there's various sensors here, systems that are feeding data back to higher levels in the factory. So you have your traditional things that you would find in a factory conveyor belt, for example, the actuation required for the belt system and the robotics, the positional, angular, voltage, and current sensing that's required for both of those systems. You've obviously got a human-machine interface, various safety systems, and then in today's factory conveyor belts, you're going to find things like machine vision systems, or RFID readers, QR scanners, and various other sensors. And all of these are increasing the number of ports, the number of devices that need to be interconnected, and each of these is increasing the number of data that needs to be fed back to the factory, as each of these are trying to interface directly to the cloud. Here we are showing a connectivity model for tomorrow's factory. Stretching from the end node of the operations layer right up to the IT layer, if we start at the end node, we can see where field bus networks are used to connect control devices to systems like robotics, drive, processing instruments, or the conveyor we just discussed. With the emergence of industrial Ethernet, we are seeing many of these field bus networks replaced or complemented with 100 megabit or 1 gigabit Ethernet networks, which now incorporate robustness and determinism to meet the requirements of the factory. For low and medium complexity sensor networks, smarter IO-Link enabled sensors can be easily connected through an IO-Link master device to an Ethernet network. And the new 10-base T1L Ethernet specification similarly provides new options for connecting direct to sensors at the end node by supporting long-range communication over a single twisted pair, similar to that used for field bus. With the requirements for more data across the factory, the intra-system networks must also be upgraded to manage the bandwidth requirements. An MLVDS, or multi-point LVDS, provides an attractive option to do this inside PLCs and distributed control systems. Now with that high-level overview, let's dive into each technology. Okay, so before we discuss the various connectivity options within the factory, it's important to look at how things are done in existing communication networks. And no discussion on today's factory connectivity would be complete without mentioning the RS-485 and RS-422 interfaces. So despite being 40-ish years old, RS-485 continues to be ubiquitous in the factory environment. It's used in the interface for industrial processing, motor control, and building automation. Much of its success can be attributed to its flexibility. So the TIA-EIA 485 standard from 1983 defines only the physical layer. So any full communication protocol can leverage this RS-485 physical layer. For example, something like Profibus in industrial communication, or Hyperface DSL in motor control, or maybe Modbus RTU or BlockNet in a building automation network. And despite being old, the various advantages of RS-485 still hold true today. It's flexible in terms of topology. You support point-to-point multi-drop or multi-point networks with up to 256 nodes. It has quite a long reach of up to a kilometer at data rates of 100 kilobits per second. And advances in transceivers today with things like equalization and extended VOD improve on the conservative estimate for this range. It is inherently very robust due to a wide common mode range and a lot of protection that's been built into today's RS-485 transceivers, things like ESD, EFT, and noise immunity. And its relative simplicity, as ORS-485 can be used with existing processor UARTs, you can use any low-cost microcontroller. There's no need for additional digital controllers to implement something like a full digital communication stack that you might need with some other interfaces, like CAN, for example. So ORS-485 would not have survived today without the improvements in transceivers offerings from off the shelf. And ADI and now Maxim combined together, these have both been key drivers in the advancements of ORS-485 over the years. And now with these combined together, ADI have the most complete offering for your ORS-485 needs for today and tomorrow's factories. The latest transceivers from ADI, they really push the boundaries in terms of speed and distance. If you look at legacy transceivers traditionally, they've kind of struggled above speeds of 30 megabits per second. Today's off-the-shelf solutions at ADI include data rates of up to 100 megabits per second, and even add things like pre-emphasis to extend cable length, so these transceivers can communicate faster and further than were previously capable with ORS-485. Some offerings include fault protection on the bus pins, withstanding up to 80 volts without latch-up or damage. So this is really for use in extreme environments. Can withstand miswires to industrial power supplies, for example, 24 volts. And for robustness, a lot of these devices integrate protection against system-level ESD, EFT, and surge to remove external components from your BOM. We've built in enhanced feature sets and intelligence. Things like auto-direction and polarity invert allow you to build more flexible and more intelligent systems. And selectable speed and termination allow your nodes to be configured at the software level and avoid more manual installation and rework. And isolation, galvanic isolation, is also worth a mention. ADI has now the market's most comprehensive portfolio of isolated ORS-485 transceivers, which leverages the combination of digital isolation and ORS-485 to provide safe and reliable communication. So here I am showing an example of our latest isolated ORS-485 transceiver. So this is a signal and power isolated device. So it features a leading ORS-485 transceiver, a 4-channel digital isolator, and a low EMI isolated DC-DC converter. And so these are the type of devices that are ideally suited for any field bus communication networks that you're designing. So following on from the ORS-485, which I'd say most people would be familiar with, we're going to just explore a different interface now, multi-point LVDS. So this is specifically designed for enhanced backplane connectivity, which we will discuss, but I also want to present it in terms as an alternative for high-speed ORS-485 interfaces. So let's take a look at that. So I think the first question just is, what is MLVDS, right? If you haven't come across it before. And really, it's best thought of in terms of a combination of the best parts of ORS-485 and the best parts of LVDS. So ORS-485, it's inherently multi-point and it's designed for communication, robust communication over long cables. But it does fall back slightly in terms of its high power consumption and its speed. LVDS, or low voltage differential signaling, on the other hand, is really optimized for point-to-point connections at a PCB level. It addresses some of the shortcomings of ORS-485 because it's high speed and low power. But again, because it's limited to point-to-point networks, it becomes less ideal when you're designing large multi-point networks or, for example, a backplane. And this is where MLVDS steps in as a newer technology option. So MLVDS, in the name, is optimized for multi-point communication, for example, on a backplane, and brings the high speed and low power capabilities of LVDS. Its key features are its ability to communicate over at least 32 nodes on a multi-point network. Each lane can communicate up to 250 megabits, depending on your transceiver. It's relatively robust with a wide common mode range when compared to standard, CMOS outputs, and it has low power consumption. So now let's look at where MOVDS can be used as an alternative to where you might be using ORS-485 in your factory today. And so if we consider on the screen here, we've got a network between a controller and, for example, a servo motor, which has a positional encoder sending information about the feedback, sending feedback on the position of the motor back to the controller. And this traditionally today is done over an ORS-485 interface. The cable distance might be 100 meters, and let's say the data rate is 20 megabits per second. Now, let's take a look at how these networks have evolved over the years. So what I've shown here is a scatter plot versus time or versus year on how the data rate for these positional encoder interfaces has increased. And you can see in the last 5 years there's really been an explosion in terms of the requirements for bandwidth. And this all stacks up with the Industry 4.0 trend for more data and more speed and more accuracy. And the problem really that we're encountering here is that there's a general trend for more speed, but ORS-485 is running out of headroom. We're hitting the limitation here of the ORS-485 physical layer. Now, while there are some leading solutions from ADI that can really push the boundary of this, with the trajectory and the requirement ever growing, eventually ORS-485 networks are not going to deliver on the speed requirements. And this is where MOVDS provides an alternative and allows a multi-point option to increase the bandwidth. And what can you do with this additional bandwidth? Well, aside from having a more accurate encoder, more bits, more positional awareness, you can also start to include more intelligence at the end node, adding things like vision sensors or temperature sensors to get more data about your end system and feed this all back to the controller over the same network. You can see that this is done over now a 200 megabits network, which MOVDS is very easily capable of. If we compare ORS-485 and MOVDS, we'll see that the maximum data rate and power consumption are where MOVDS brings its advantages. It is worth noting that the minimum output voltage has reduced versus ORS-485, and your distance and number of nodes is a bit limited when compared with the traditional ORS-485 network. So that was an interesting use case where you might be using ORS-485 today, but let's look at the end application where MOVDS was originally designed. And this was in, for example, a backplane and something like a data acquisition rack. So you can see here we've got a bunch of assets or end nodes, sensors at the end of the factory, and we've got a data acquisition rack that needs to communicate with them all. This is communicating via Ethernet as expected up to the cloud or a server. And it's communicating using analog I/O devices to each of the end devices. So the rack needs to aggregate all this data from all these end devices and feed it back up to the cloud via Ethernet. And how do all of these devices communicate with each other? Well, it's over some type of backplane is how this is done to date. And what we're presenting here is how MOVDS connectivity is an ideal option for tomorrow's backplanes. The speed advantage of MOVDS makes it ideally suited for programmable logic controllers, condition-based monitoring, or any distributed computing systems that use a backplane. And for example, by extending the backplane over Ethernet to a second rack, you can imagine where you have additional devices connected. Go a little bit deeper into this now, and we'll look inside the rack. And we'll see why MOVDS is really suited for these backplanes. So first off is the high bandwidth. You can see here on the right, we've got 250 megabits per second backplane, which is significantly faster than something like an SPI or a CAN-bus-based backplane. We have the ability for multi-point where all of these devices are connected together on the same bus, so you're allowing communication between any node all over the same differential pair. And this can have up to 32 cards in a backplane, which meets, really any requirements in an industrial rack. For more bandwidth, you can just aggregate lanes. So add more lanes in parallel, and you get more bandwidth. So for example, quad lane, you get up to 1 gigabit bandwidth by combining 4 lanes. And these devices are designed for low power consumption, so trying to keep the heat down in the chassis is really important. So even with these multiple transceivers, multiple lanes, and high-speed communication, you can do this while maintaining a reasonable temperature within your chassis. And of course, reliability, developing robust systems is very important. So at the card level, you can see the module card here, which include, say, a CPU, the MLVDS PHY to communicate to the backplane, and then the I/O to communicate to the edge. This is where MLVDS brings advantages in, for example, hot swap for live insertion and removal when the backplane is powered. The transceivers themselves are robust against ESD protection because the cards are going to be handled manually by operators. And the receivers in MLVDS are designed to fail safe. So in the case where the backplane decides to behave in an erroneous way, or for example there's some short or something like that, you know that the receiver will pick this up and behave in a deterministic, defined way so that you can make the correct decision about what to do at the I/O level to your instrument at the edge. And lastly here, I'm just going to present some options that ADI has in terms of MLVDS transceivers. So we've got a comprehensive family of both full and half duplex single transceiver devices. These are optimized for low power consumption, and they do this in compact packages. Their timing performance is very good, so we have low latency, skew, and jitter performance really for when you're seeking that optimum signal integrity on your backplane. And as I mentioned, hot swap and system level ESD really helps you build your robust end systems. And some other key benefits that are worth mentioning are the extended temperature range for, again, when that chassis starts to get really hot. And just throwing back to what I said on the last slide about aggregation of multiple lanes, we also have quad transceivers where one of these devices will enable you to have a combined bandwidth of 1 gigabit per second on your backplane. Okay, so now that we've looked at some of the more traditional approaches for communication within a factory, let's hand over to Conrad to learn about new exciting ways to connect with devices that are at the edge of the factory.
Thank you, Neil. Let's talk about IO-Link. Before we dive into the details, let's have a quick look on the old school sensor. So here on the top left, you see an analog sensor. So for example, if it's a PT100, and there's an A to D conversion, and the microcontroller will calculate the temperature from that result and drive a D to A converter to provide 0 to 10 volt or 4 to 20 milliamp that travels over the long cable to the PLC, again into an analog input. You see here, if noise is introduced, it would directly affect the measurement. Also, there are binary sensors. For example, if you have a thermal element, if it's above the threshold, the level will be high. If it's below the threshold, the level will be low. And that directly feeds into a digital input on a PLC. So here, noise is less of a concern. However, you see with both of these, there's only unidirectional communication. So if somebody wants to change the thermal threshold, you will have to physically walk up to the floor and turn the knob. Also, you see there's only one data point that is transferred, so there's no way to get any additional information like diagnostic data. This picture shows you a system architecture example. So it shows you where IO-Link is located at the factory floor. It's not a field bus, but it's field bus agnostic. It's using a simple 3-wire unshielded cable. However, the communication is bidirectional, so it allows for configuration and additional diagnostic data. On top of this, there's an IODD file, a device descriptor file, which supports the user to install, and also simplifies significantly the configuration and installation. Where is IO-Link used? It's mostly used in industries where frequent changeovers are happening or where downtimes are a big concern. Also, wherever you have small batch sizes, the goal is often to have to be cost effective as sample size 1. And basically you see it in these standalone robot cells or smart manufacturing lines. The IO-Link standard is an open standard, and it was established in 2009. ADI was in the consortium since it was established. And you see right now in the last 2 or 3 years, it's ramping significantly, even despite of the COVID pandemic. This picture shows our IO-Link demo system. So it also gives you a rough idea how IO-Link could look in the field. In the center here, you see our IO-Link 8-port IO-Link master. There are also options with 4 or even 16 channels. These masters then connect to multiple sensors and actuators, which are usually in relatively close proximity for up to 20 meters. So the key challenges with industrial sensors in general are heat and size. They must be small enough to fit onto the factory floor and at the very edge. Usually they are looking exactly like this picture you see here. They are similar size to the cable connector. And since there's only a tiny housing, there is not much space to dissipate any heat. So they have to be very small and very efficient. But at the same time, you cannot compromise robustness or performance. So still you need to survive ESD, EFT, and in some cases even surge protection. And also, of course, you can still have to drive the current and necessary power. This is how we address those items. This is one of our device transceivers. So you see that inside a device, a sensor basically, or an actuator. The key important pieces are here. The output driver is very low on, so it's very efficient. And we integrate everything that is needed inside a sensor and actuator. So we have a DC to DC converter, we have multiple LDOs, and we even integrate surge protection. So we have TVS diodes integrated. And all this comes in a very small package, which is 2.5 by 2 millimeter. You see we have multiple different flavors, some with DC-DC, some without, dual and single channel. This is one of our IO-Link master transceivers, the MAX14819. It supports 2 full channels. Again, it's very efficient. The R1 of the output driver is only 1 ohm, and the total power consumption for the 2 channels is 1.9 milliamps. It integrates everything that is needed for a full IO-Link port. So even the L+ controller, which provides power to the sensor, and also a frame handler, which significantly offloads the microcontroller because it handles entire IO-Link messages rather than individual bytes. All field side pins support reverse current blocking, over voltage protection, and over current protection. We also have 2 additional type 1 or type 3 digital inputs, and they are fully compliant to the IEC standard as well as the latest IO-Link standard.
Thank you, Konrad, for taking us over the IO-Link section. And now I'm going to introduce to everyone the industrial Ethernet technology, which not only allows connecting the end node, but you can connect all the way to the cloud, allowing seamless connectivity from cloud to end node. So the first question is, so why industrial Ethernet? Well, the first big advantage is that everything from cloud to edge uses the same technology, the same type of package, which is Ethernet frames, independently on the protocol that runs on top of it. And that's what we call seamless connectivity, right? And because it's based on IEEE standards, the technology offers interoperability across all vendors. Now, in terms of reach, wired Ethernet can cover distances of up to 100 meters for traditional Ethernet and up to 1 kilometer in the case of the newer 10x200 standard. Now, one of the first things that come up to my mind when I think about Ethernet, wired Ethernet, is speed, right? Big data. And this is because Ethernet enables speeds from 10 megabit per second to gigabit per second, while maintaining a relatively long reach, or long reach in the case of 10x200, which is a huge advantage over other communication protocols that only allow, speeds from kilobit per second to sub-megabit per second. Now, as we know, one of the keys for Industry 4.0 is the increase of data, right? From the operational technology to the informational technology. Now, at the informational technology, we can drive analytics that can be used to increase productivity and efficiency in the factory, plus being able to transmit not only the sensors data, but diagnostics data that can help, schedule preventive maintenance when required, can reduce or eliminate downtime. Now, one more thing that I want to mention here is that Ethernet provides deterministic timing, so almost real-time timing or real-time timing. And many applications, for instance, motion control, require time-aware network, that satisfy the deterministic timing to ensure the correct operation of some processes. And a standard Ethernet cannot guarantee that, but industrial Ethernet does. Now, someone could ask, so how so can Ethernet be deterministic if when, connecting to the internet, sometimes loading website takes a variable amount of time, and sometimes even not even load a website when the connection is not good? And the answer is, well, traditional Ethernet does not, but industrial Ethernet does. And does it by using low latency PHYs, physical layer devices, in addition to something called time-sensitive networking, also known as TSN, which makes industrial Ethernet a real-time communication protocol to guarantee latency and determinism. Now, because of the increased data throughput, industrial Ethernet can be used in different topologies and not just point-to-point. For instance, line topology or ring topology. In the picture in the left, we have line topology, and it is easy to see that to continue adding more robots to the network, well, all we need to do is add the fourth robot there and then a wire to robot 3. Now, the latency that robot 4 is going to experience is going to be the combination of the latencies of all the nodes. And so having a low latency is key, and that's something that Analog Devices has taken into consideration to ensure the performance in time-critical applications. Another important thing is power, and Analog Devices has taken it very serious as well. And one of the things that is important about power is that by having low power physical devices, more power can be available for the processing, and also less power is dissipated. And this last point is quite important for devices that operate at high temperatures, say for instance at 105 Celsius, because then we don't have to worry about anything overheating around the physical layer device. Let me now introduce you to ADI Kronos, which is Analog Devices' comprehensive suite of Ethernet solutions that includes physical devices, physical layer devices, embedded switches, network interface platforms with complete protocol support. And all of that provides deterministic timing, robustness, scalability, flexibility, and complete solutions that simplify your system design. So the first technology I'm going to talk about is 10BASE-T1L. Now, what is 10BASE-T1L? Well, 10BASE-T1L is the standard that defines the Ethernet physical layer that enables the communication over a single twisted pair of cables of up to 1 kilometer at 10 megabit per second data rates. So being single twisted pair could potentially enable using the existing cable infrastructure, which otherwise would require costly investment in a factory. Now, comparing 10BASE-T1L to traditional Ethernet, traditional Ethernet uses 2 or 4 pairs of wire. 10BASE-T1L uses only 1 pair. Traditional Ethernet reaches up to 100 meters as per the standard, while 10BASE-T1L can reach up to 1 kilometer. The speeds at which traditional Ethernet transmits its data is from 10 megabit per second to gigabit per second, while 10BASE-T1L is fixed at 10 megabit per second. And a very important factor here, a very important aspect of 10BASE-T1L is that it's compatible with intrinsic safety, which means that this can be used in zone zeros of process control, so explosive environments. Now, talking in the context of process automation, process control, the current systems are mainly implemented using 4 to 20 milliamp loops, which requires a dedicated cable for each end node all the way to the PLC. Now, this has many disadvantages and can become a complicated network quite fast given the amount of cables required, as it can be seen on the picture on the left. Now with 10^T1L, the picture on the right, the network can be simplified as shown, where a single pair of wires can be used to transmit data from different sensors given the increased bandwidth of each link. Now additionally, Ethernet frames are transmitted from the cloud to the edge, which allows for more information from the sensor to be sent to IT, such as diagnostics, so allowing seamless edge-to-cloud connectivity. Now in terms of scalability, if we were to add another sensor to the diagram on the left, as I said, we would have to add another wire all the way from the sensor at the end node all the way to the PLC, while adding another sensor on the diagram on the right with 10^T1L would just be adding the sensor A and a small wire to the closest switch. Now again, for process control in other applications, ADI has two main offerings for end nodes and field and power switches. The ADIN 1100, which is the 10^T1L PHY, and the ADIN 1110, which is the 10^T1L MAC PHY device, which has a 10^T1L PHY and a MAC integrated in the same chip. Now let's take a look at both side by side. So let's take a look here, and the main difference, as I said, between the ADIN 1100 and the ADIN 1110 is that the ADIN 1110 has a MAC in the same chip, which simplifies the digital interface of the host processor, which only requires to have an SPI interface, so a serial peripheral interface. Now, for you to use a PHY-only solution, meaning the ADIN 1100, the high-performance host processor must have a MAC, or an external MAC must be provided, and it can be interfaced through MII, RMII, RGMII, while managed through MDIO interface. Both, though, keeping a low power consumption and high performance. Now, the third product I'd like to introduce to you is the ADIN 2111, which is our two-port low complexity switch. And now, this is basically two 10^T1L PHYs in a single chip, compliant with the IEEE standard, and an SPI that supports 10 megabit per second full duplex communication. And it can be configured for cut-through or forward operation, which means that the packets received in port 1 can be automatically forwarded to either port 2 or SPI, and the same applies for port 2. So it is really a three-port switch, between the two 10^T1L PHYs and the SPI. Now, in building automation, this device can simplify your design and can be utilized to implement line and ring topologies like in the image here on the top right. This is really, as I said, a three-port switch, as data can be switched to and from either of the ports, including the SPI. And again, this is done while keeping a quite low power consumption and a small package for more compact system design. Quite often we get a question in regards to cables. And for a given cable, can I achieve 1,000 meters of communication? And the cables are specified in the IEEE standard, in the 802.3 CG standard. But unlike traditional wired Ethernet, where the cables are well defined, the only characteristics that are specified in the standard for 10^T1L are the impedance of the cable, the maximum insertion loss and return loss, the maximum link delay, and conversion mode for unshielded cables, and also specifying that you can have up to 10 inline connectors on the same cable link. Hence, a wide variety of cables can be supported as long as they meet those characteristics. And talking about cables, with a long cable of up to 1 kilometer, there's obviously a huge challenge when a fault occurs. We know those cables are exposed to quite harsh environments where corrosion can build up, humidity can accumulate in any of the connections or junctions, or a sharp edge can eventually wear off the cable, producing an open or short. And so Analog Devices products offer a set of diagnostics tools and make the job of debugging those issues easier. These that we offer are the signal quality monitoring, loopback modes, frame generator and frame checker, and quite importantly, a time domain reflectometry engine that allows highly accurate open and short fault detection with a distance to fault better than 2% of error. So if a fault occurs, we can run our time domain spectrometry engine and find where exactly it occurs within 2% of accuracy. So to summarize the 10BASE-210 portfolio for analog devices, we offer solutions for flexible system design with ultra-low power that leverages a proven solution compliant with the 10BASE-210 standard and allowing communication for over 1.7 kilometers, which offers enough headroom. We increase flexibility, design flexibility by providing a PHY chip, a MAC-PHY, and a low complexity switch for easy implementation of line and ring topologies. And we reduce debug work and effort, providing a full suite of debugging capabilities such as TDR, frame generator, frame checker, and so on. Let me now introduce you to the 10BASE-T, 100BASE-TX, 1000BASE-T Ethernet. The products I'd like to introduce now are the ADIN-1200, our 100 megabit per second fast Ethernet PHY, and the ADIN-1300, which is our gigabit Ethernet PHY, which are both industrial-grade devices that ensure low latency, low power consumption, both in a small package for more compact design, tested for temperatures from -40 degrees Celsius to 105 degrees Celsius for the harshest environments, and tested for EMC standards such as EFT, ESD, and so forth. And all of that ensures the highest performance and robustness even in the harshest environments. Now, if what you need is to simplify your design and development, we provide a full system solutions that have the necessary hardware and complete pre-certified software, which is very important, needed for the network protocol of interest, for instance, EtherCAT, Profinet, etc. And we call this the RPG2 platform, which is a two-port multi-protocol platform based on the 100 megabit per second ADIN-1200 PHY. And this is in a small factor for embedded applications that ensures low power and low latency. And for that, we provide the driver for the host microcontroller to interface to the RPG2 platform. And now this can be used for factory and process automation, motion control, building automation, and transportation. And as this product is pre-certified, we are simplifying the development time and hence, reducing time to market. And now, the two ways how we can provide this is as a reference design or an off-the-shelf module containing all the hardware needed and ready to be incorporated on your platform. And this is what we call the ADIN-2299. So for R&D, you can use the ADIN-2299, and then you can use it for production too, or implement the embedded reference design in final production. Now, up until now, we've been describing edge and field communication technology, and now Neil will take you over connecting to end equipment.
Okay, thanks, Hector. So now let's take a look at options for isolating USB, which is really a way to provide a robust peripheral interface to any of the pieces of equipment that would exist on your factory floor. So, USB in industrial systems, what is it? Why we would use it? We're all familiar with USB. It's in our daily lives, but maybe a little bit less familiar with isolated USB and its use in industrial. So, in most industrial systems, there are debug ports that exist, and historically these would have been serviced by the RS-232 connector that we all know and love. And so USB has done a great job of kind of replacing RS-232 as the de facto port on any systems for debug, data logging, and firmware updates. The challenge is with industrial systems that things like noise immunity and electrical safety are critical. You have ground loops and noise sources that can be introduced at any port or cable. And with the high voltages that are present in industrial systems, particularly motors and etc., the safety of operators on low voltage electronics is paramount. So this is where isolation comes in. By isolating a port, you can provide a safe and robust interface against noise and high voltages. And so ADI's first to market solution back about 10 years ago, we released the only USB isolator on the market that serviced the USB 1.0 and 1.1 standards. And this was useful for low speed and full speed USB, which is 0.5 megabit and 12 megabits per second respectively. Very useful for attaching peripherals like mice, keyboards, and for slow speed updates, and also with a debug port. But it falls short where you need higher bandwidth, and this is primarily for things like updating software where you have a lot of information you need to transfer, maybe a bit more intensive data logging where you're capturing a lot of information, or where you want to do something like stream video. And so we're delighted to announce our second generation USB isolator has released this month. And so keeping the backward compatible support for low and full speed, we now support high speed 480 megabits USB 2.0. For really the key benefits of this are faster firmware updates. We can now open up new use cases for the case where, say, machine vision and you want to isolate a USB stream to a USB video stream. And as we'll see, the benefits that come with this product also bring more flexible options and enhance robustness to your systems. So this is the product. It's our second generation USB isolator. It's the ADUM 3165 and family. There's 4 generics in total. I'm just going to highlight some of the key features here. The most important one being the support for 480 megabits data rate in both the upstream and downstream direction. And this is useful for software downloads and video streaming applications. There's also retiming built in. So with the high-speed 480 megabits, meeting USB compliance is a big challenge. And so we've built in a retimer to try ease that burden of the customer. And so all the data is retimed and you get a completely clean eye out the side where the data is retransmitted. In general, we've also boosted the feature set. We support the USB low power and suspend modes, which is really important for battery-powered peripherals where you want to minimize power consumption. And the speed is auto-detected between low, high, and full speed, so no pin strapping is needed. And we also have a downstream power good indicator. And just in the general functionality of the product and the isolation barrier, we've got an extended temperature range support, and the isolation barrier supports 8 kilovolts contact across the barrier for IEC, ESD, as well as the market's first 20 kilovolt surge protection. And we put a big focus on our new products, so meeting Class B requirements for EMI and for stringent standards like CISPR 32. And as well, on the upstream side, we've also built in robustness features like short circuit protection on the upstream side. So here's just a little bit of the product in action. This is our off-the-shelf evaluation board that you can purchase from the Analog webpage. You can see here it's connected basically from a USB host device like a laptop to a flash drive. And this is showing the 480 megabits streaming of high-speed data. So you can see on the top there the approximate 60 nanosecond delay from when the top 2 traces, which come in on the left side of the device, get repeated out to the right side of the device. And as I mentioned, signal integrity being so important, you can see the eye diagram here and how there's loads of margin at 480 megabits because of that retiming feature that we've built in. And so as I mentioned, this is a 4 generic family. All products are released and available on the web now. And so we have 2 package options, large package for higher isolation ratings and a small package for space saving. We also have options for a host or peripheral device. So this table will help you identify the best device for your application. So a quick recap on what we covered today. Starting at the edge of the smart factory, Hector and Conrad have discussed exciting new options for connectivity right to the factory edge in IO-Link and 2-wire Ethernet. Hector has discussed how industrial Ethernet is enabling the backbone of connectivity between the factory edge and the IT layer. We've shown some new enabling technologies with the market's first high-speed USB isolation, as well as ways you can future-proof your more traditional backplane and fieldbus networks using the latest RS-45 and multi-point LVDS solution. So ADI has you covered for all your connectivity needs, whether you're designing your next smart factory or retrofitting the intelligent buildings of tomorrow. So take the next step and learn more about these solutions by clicking the relevant links below. And with that, this concludes our presentation. Thank you for your time today.